We are Team ABCA, and we would like to present our approach to the topic of to design a program that outputs the solubility of the compound. Hope you enjoy it. What is solubility? Soluble and insoluble are relative terms. To exemplify, no metallic salts are absolutely insoluble in water. For example, even lead carbonate, which is regarded as insoluble, dissolves to a very small extent in water. Solubility is the relative ability of a solute to dissolve into a solvent.
This is our initial model. We tried to classify compounds by starting with the obvious differences such as states of matter. VSEPR was a big part of our initial model as we thought polarity would have the greatest effect on solubility. VSEPR was also used in order to implicate variables such as bond angles. However, the solubility trend was much more complicated than we thought it would be. Therefore, we had to look in a greater depth in our next model, grouping compounds into as many solubility trends as we could find.
So our classification system, we can see that many compounds have different trends when coming to the relationship of temperature and solubility. This is why we have chosen to group compounds with similar solubility trends to enhance the accuracy of the model. How we grouped it can be seen here. The variables we use for our final model. So we used molar mass, the state of matter, the temperature, the connection map, intramolecular bonds and intermolecular bonds, and the product species in order to decide which classification that the compound comes under.
Mass itself is not a major factor in how soluble a substance is. However, when comparing compounds of the same type, higher molar mass compound will be less soluble than the lower mass compounds. Since mass is proportional to volume, the charge density is bigger as mass increases. Hence, the solubility of compound is lower. Overall, the solubility value will need to be varied with molar mass.
States of matter. For solids and liquids, the solubility tends to increase along the rise of temperature. The increase in kinetic energy allows the solvent molecules to more effectively break apart the solute molecules held together by intermolecular attractions. For gases, the solubility decreases as temperature increases. Increasing temperature increases the kinetic energy.
Solubility usually increases with temperature. When a solid dissolves, its component ions diffuse into a greater volume of solution, carrying their thermal energy along with them. Hence, the entropy increases.
There are two forces, which are intramolecular and intermolecular, that operate in a molecule. Intramolecular forces are the forces which hold an individual molecule together. Intermolecular forces are the forces between one molecule and a neighboring molecule. The types of intramolecular bonds are polar covalent, nonpolar covalent, coordinate covalent, ionic, and metallic.
For diatomic covalent compounds, we grouped separately due to their different structure in the connection map. Looking at diatomic molecules, we are easily able to assess the polarity without the use of electronegativity values. Although the level of polarity may be difficult to find, the use of polarity in determining the solubility of diatomic compounds will be easier. We can suspect that the polarity of the compound will be higher when there are bonds with greater electronegativity difference.
Nonpolar covalent forms when electrons in the covalent bonds are shared equally between the two atoms. The distribution of electrical charge is then balanced. Compounds with only nonpolar covalent bonds hold weak or no dipole moment, hence it makes it harder to dissolve in water.
The intramolecular bonds. Coordinate covalent bonds, which are also known as dative bonding, forms when electrons in covalent bonds are shared from the same atom. These are sparingly soluble in water, and the solubility trend with temperature differs depending on their state.
Ionic bond is the electrostatic attraction between oppositely charged ions. Increasing temperature usually increases the solubility of an ionic compound. Despite there are some exceptions, most ionic compounds are soluble in water. Metallic bonds are the electrostatic attractive force between positively charged metal ions and the delocalized electrons.
Intermolecular bonds. London dispersion. London dispersion forces are the weakest intermolecular forces that always exist. This force tends to be stronger between molecules that are easily polarized. The larger the size of an atom, the greater the London dispersion force is. This is because the heavier atoms have more electrons, meaning that the valence electrons are further away from the nuclei, which makes it easier to form temporary dipoles and to polarize.
Dipole-dipole is the interaction between two polar molecules. The negative portion of one polar molecule attracts a positive portion of an adjacent polar molecule. Hydrogen bonds are formed by hydrogen and either N, O, and F. This force is the strongest IMF, hence it exerts the highest effect on solubility.
These are important details of our model. Some connection mats have 2 atoms, whereas some are made of 3+ atoms. In order to avoid errors when utilizing the connection mats in our program, we have made sure to treat the 2 types of connection mats differently. This also benefits us in estimating the solubility of inorganic and covalent compounds.
By having a relatively simple algorithm of dividing the hydrates from the other compounds at the start, we were able to reduce the number of compounds having to go through heavy algorithms, therefore reducing the runtime of the program. We decided to separate hydrates in our model due to their distinctive trait. Hydrate is a compound that contains water in the form of H2O molecules. These water molecules can be typically removed through heating, called dehydration. Hydrates are usually very soluble in water, and usually involve ionic compounds with transition metals as the cation. The water molecules inside the crystals of a hydrate mostly make coordinate covalent bonds and hydrogen bonds to the cations of the salt. Hydrates are generally expected to be thermodynamically more stable, hence less soluble and slower to dissolve than anhydrase forms above the critical water activity for hydrate formation. However, as particle shape distribution, specific surface area, and other surface properties heavily affect the dissolution, hydrates may dissolve faster than anhydrates.
Ionic compounds are firstly grouped according to the groups in the periodic table. In addition, we have considered the solubility rule. Ions not in the solubility rule have been grouped with ions with similar characteristics, such as charge, size of ion, and solubility strength itself.
By grouping the ionic compounds into groups of similar solubility trends, we have created a scatter graph using data we have found from the internet. We made sure these data were reliable by checking the source, if they did follow the trend, and if they had 1 atmospheric pressure as a condition. By plotting a scatter graph, we drew a graph of best fit from the variables of solubility and temperature, and have found the equation of the graph which would be integrated into our model to be used accordingly.
The magnitude of charge puts into consideration the size of the electrostatic force between the ionic compounds. The solubility of salts also depends on the mismatch between cation and anion radii, which can be concluded from observations of the Born-Haber cycle. The solubility depends on the entropy change for the overall cycle. Here, we need to consider the trends for both the lattice energy EL and the hydration energy HH. For salts that contain large anions, lattice energy doesn't change much as R plus changes. Because the anion dominates the R plus plus R minus term in the denominator of the formula for lattice energy. On the other hand, hydration energy changes substantially with R plus, especially for small cations. For small anions, lattice energy is much more sensitive to R plus, whereas hydration energy does not depend on R plus as strongly. Putting both trends together, low solubility is often encountered when the anion and cation match well in their sizes, especially when one or both are multiplied charges.
Looking at the graph on the left, the large SO4 minus ion is size mismatched to small cations such as Mg2+, which have large hydration energies resulting in soluble salts, with larger cations such as Ba2-, which have lower hydration energy. The lattice energy exceeds the solvation enthalpy, and the salts are insoluble. The graph on the right shows the case of small anions such as F- and OH-, where the lattice energy dominates with small cations, Mg2+ and Li+. Anion-cation size mismatch occurs with larger cations such as Cs+ and Ba2+, which make soluble fluoride salts.
Polar covalence. Polar covalent forms when electrons in the covalent bond are not shared equally due to difference in electronegativity. Due to the formation of dipoles, an overall dipole moment is formed.
For other covalent compounds, we have set numeric values for each forces bonds present, with hydrogen bonds being 40, dipole-dipole forces being 25, London dispersion forces being 10, coordinate bonds being 18, polar covalent bonds being 15, and non-polar covalent bonds being 5. Additionally, molar mass of the compounds were taken into account. The value that accounts for molar mass was calculated through an algorithm. Using these values, we have calculated a variable which we called the solubility factor.
Using the three variables, solubility factor in the x-axis, temperature in the y-axis, and solubility in the z-axis, we constructed a data table and extracted equations relating them. We set up a few sets of parameters and constructed a 3D graph considering the state of matter and trend that compounds show. By using the most suitable graph, our model would be able to extract a relatively accurate solubility value.
Organic compounds are compounds based on carbon. We decided to separate these compounds in our model because the properties of organic compounds are very different from those of inorganic compounds. Properties of organic compounds are that they can be gases, liquids, or solids at room temperature, and they are mostly nonpolar, which means they are difficult to deduce an exact solubility value, and they have weak intermolecular forces.
By using the connection map, we can distinguish between inorganic and organic compounds. The condition for this to be true will be when a carbon atom is next to a hydrogen atom in the connection map. For other hydrocarbon derivatives, there will be extra conditions to be satisfied.
We first grouped the compounds into alkane, alkene, and alkyne. Then we have considered the number of hydrogen bonds in the compound, with one hydrogen bond being monomers, two hydrogen bonds being dimers, three being trimers, and compounds with more as polymers.
By using the hydrogen bonding and other intermolecular forces, we can predict the solubility of organic compounds. The more the forces present, the higher the solubility factors that affect van der Waals forces are: length of organic molecule, branching, and presence of O and F or electron-heavy atoms. Longer chaining organic compounds mean greater surface area, hence there are more intermolecular forces present. Similarly, the more branching there is, the more interactions between the molecules. Lastly, electronegative atoms interact with hydrogen atoms in the water and form hydrogen bonds, affecting the solubility.
Without the use of bond angles, we were able to reduce runtime massively. This is because we have planned to use VSEPR shapes for our covalent compounds, but have found out that the complexity of our algorithm would have brought us points down assessed on runtime. The accuracy of our model has been leveled down due to this issue. However, it was necessary to abandon the complex code in order to attain our needed points for reducing runtime from our program have been believed to be attained.
To the Python implementation of this model. The approach we used is we chose to create a class for the compound and use object-oriented programming to create functions to recognize whether it's a hydrate species, whether it's a organic, inorganic, ionic compound, things like that. The trade-off for runtime is insignificant, and in the long run, were this code to be built upon, it will create readable code that can be built upon extremely easily as compared to a procedural approach where everything is in one file, which makes it very hard to read and edit. So, methods to optimize runtime. When comparing one variable to a multitude of other values, it is a lot faster to use the match case statement than to use if statements to compare. This is because the if statements compares two variables every time, whereas the match case statement stores the value of the variable that we are comparing and simply compares that value to the rest instead of accessing the compared value every time. Additionally, since we're using functions, else statements are often not required. This is the case when the function will return a value if the criteria is met, and the rest of the function is then simply not ran. In this case, it is a lot faster to treat any piece of code after the if return statement as an else statement instead of having an else statement. This will become clearer in the example. The use of dictionaries to directly correlate one variable to another will also aid in reducing runtime because this avoids having to compare variables, and instead it is a preset direct correlation, which is faster because it's a built-in function in Python, which I'll come on to later. We also only looked at variables when it was necessary, and we did not do any pre-processing, reducing the runtime. A note is that the pre-processing is only done when we know that multiple functions will be using the same pre-processing or accessing the same thing, so then we can do that beforehand, but otherwise, no pre-processing is done. We also look to use built-in Python functions over our own user-defined functions where possible, as the built-in functions are written in C, and so they are a lot faster than compared to a function written in Python because of the way the Python language is written. Here are some examples. As you can see, match element to, and then the case statement, as mentioned before, this is a lot faster. This is an example of if else, not using if else, and instead just using if. As you can see, as you can see, for the first line, if it returns something, then nothing else is ran. So if it doesn't return anything, then that is equivalent to an else statement anyway. So this improves the runtime. And thirdly, dictionary. Here I use a dictionary. Here we use the dictionary to correlate the intramolecular bonds to a specific value. And by using this, it avoids using any if statements, which makes it a whole lot faster to run the program, which improves the runtime. Thank you.
Applications to the real world. Lab scientists can use our model when conducting experiments, which relates to solubility. Solubility values can be either an independent variable or control variable for various experiments. If the solubilities of compounds act as an independent variable, determining the exact values and knowing the difference between them will allow scientists to analyze the results more accurately. Moreover, the scientists can adjust the solubility of the compounds for better accuracy.
When the temperature of a river, lake, or stream is raised abnormally high, usually due to the discharge of hot water from some industrial process, the solubility of oxygen in the water is decreased. Because fish and other organisms that live in natural bodies of water can be sensitive to the concentration of oxygen in water, decreased levels of dissolved oxygen may have serious consequences for the health of the water's ecosystems. In severe cases, temperature change can result in large-scale fish kills. Therefore, whenever there is a huge change in the populace of sea animals, the marine scientists may use this model to calculate and evaluate the solubility of the bodies of water and find out the reason why such things happened. Then they can research into how to increase the solubility of oxygen in the water back into the normal state to obtain a stable ecosystem. Okay, thank you for listening to our presentation.